Okay, I will give it in English, okay? So, actually, I want to go, this seminar, I want to go back a little bit what I did more or less during my thesis, which was on reactive transport models. And there is something which I call components. Okay? And we can do very nice things or nasty things with components. Okay? So just a little bit of the previous work. Okay? What I did during my thesis was a sort of elimination of minerals. Okay? And actually, I should say it's not elimination. Actually, it's better to say decoupling. We don't eliminate it, actually. We don't have to eliminate. And then there are some other work by Sergio Wiens and Serge Project that did something on how to decouple components. Okay? And then we can also use some of the things that we developed by decoupling to get a sort of analytical solution or semi-analytical solution. I think the most famous one or the most cited one is the one by De Simone. Okay. And we can use it, for instance, to develop semi-analytical solutions for calcite dissolution, which has been quite a lot, but also used for the CO2 storage. And we can also add a little bit of kinetics. Okay, that is done by Xavi Sanchez, and actually also the latest by me and by Paula. So in general, if we think a little bit about these decoupling of components, we can use it to do nice things. Okay? But for these applications was sort of for particular cases, calcite dissolution, carbon oxidation, etc. Okay? And what I like to do now is to get a little bit more of a generalization and to also look how far can we go. Okay? That is a little bit the objective of this seminar. Okay, so just a little bit of theory, okay, about components, what you have to know. Yeah, I always use matrices. And matrices are just boxes with numbers. Okay? So here's and one. Let's give an example. Rows, columns. We put numbers in these things. And one important concept, is the rank of the matrix. Okay, so the rank of the matrix is just an example. I think it's the most illustrative. So we have this is in the matrix, and actually there are two independent rows. Okay? These two over here are independent. The third one is not actually it depends on the other two because I can just sum the first two rows to get the third one. This means that this is not another independent row. Okay? And also, if we have only zeros, this doesn't count either. Okay? So the rank of this particular matrix is 2. Okay? Because we have 2 independent rows. That's just the first thing. The second thing is what we call a kernel. Okay? Also sometimes called null space. Okay? It sort of expresses orthogonality. Okay, so things that are 90 degrees one of each other. Okay, so here's an example. We have this matrix that we had before. Okay, but only the two independent, two real independent rows. Okay, and I can say actually these are two two vectors. 0 to 1, 1, 1, 0, 0 to 1, 1, 0. This is 1, 1, 0, and this one, the other one is 0 to 1. Okay, so I got two vectors. And of course, if you have two vectors and the origin, let's say the 0, 0, 0 point, I can put a plane on these two vectors, because I have 3 points. Put a plane. Now, of course, I can define something that is perpendicular or orthogonal to this plane, which is this red thing, this red line. And the special case is that if I call this blue thing U and this red one S, then if I multiply this U times the transpose of the S, I always got 0. Simply, if I do U 0 to 1, 1, 1, 0 times 1 minus 1, 2, okay. I got this times this is 0, this times this minus 2, plus 0, and the second 1 times 1 is 1, 1 times 1 minus 1, so 1 minus 1 is 0. So I always got 0. Okay. Now another important thing is that if I have, let's say, in a 3-dimensional space, I got a 2-dimensional blue space, okay, then I can have a 1-dimensional red space, okay, which is perpendicular. So it can be deduced that the dimensions of my blue space plus the dimensions of my red space is the total number of dimensions. So 2 plus 1 is 3, and in 3 dimensions. 2 times 1, the red one is one dimension, it's a line. The other one is 2-dimension, a plane. Okay? So 2 plus 1 is 3. Okay, that's the most difficult part of my talk, I think. 1 plus 2 is 3. Of course, we can extend it. I can wave my hand a little bit if I have 28 dimensions. If I have 28 dimensions, and I got my one space. This, for instance, the blue space is 20 dimensions. Then I can have another space perpendicular to that, or orthogonal to that, which has to be 8 dimensions. Plus 28 is 20 plus 8. Okay? Okay, that's the theory. And now we go to apply this to reactive transport and chemical reactions. Okay? So I define what's called the stoichiometric matrix. Okay? So actually all the reactions, I first divide it into equilibrium reactions and kinetic reactions. Okay? So the rows represent reactions. Of course, what species are reacting are put as columns. And then maybe I have some species that are liquid, other species that are in the gas phase, and others are, let's say, in the immobile. Okay? So I actually differentiate between species of different mobility. Okay? This is important because the liquid species, they move, they are transported different than the gas phases, immobile phases. The immobile phases don't move. They are immobile. And then I can make a mass balance of each species Okay, and I put this as a vector of concentrations, and this is transport. Okay, transport thermals. And then I just have to have this stoichiometric matrix times the rate, the reaction rate, the equilibrium reactions, and kinetic reactions. And the kinetic reactions are a function of concentrations, and is different from the equilibrium reactions. I have to apply the mass action formula. Mass action. It's also in the stoichiometric matrix and the vector of activities. Okay, so this is more or less the general notification, but I don't want to explain too much detail. I think this is just some mass balance. The important thing is these stoichiometric matrices. So what we usually do is I want to get rid of this term, and so I multiply what is a component matrix, and I define this component matrix in such a way that U times SE transpose is 0. Which means that this matrix U is perpendicular, is orthogonal with the kernel of this stoichiometric matrix, the only the equilibrium. And then I just got rid of this okay, and so this RE I don't need to. So that's the trick. Of course, I can also do, for instance, multiply the U, or I can divide this U into a part of the liquid, the gas, and the immobile. And I can also define concentrations of a component in the liquid, gas, and immobile. Okay, this is very abstract, etc. So, just an example. Typical small chemical reactions. So I got CO2, which can be the liquid and gas phase, dissociation of water, and I have the carbonate chemistry. I also have calcium. And maybe I also have a kinetic reactions. So these are all equilibrium fast. Okay. This is slowly. So I have some kinetic rate load that says how much SE to silicate is dissolved. Okay. And this is my stoichiometric matrix. So I have my first reaction, CO2 gas, is formed by CO2 in the liquids. And we have water. It's the element on the left side, it's a minus, which gives H plus OH minus. And then for the other reactions. Okay. And here the last one, that is kinetic, the first one by equilibrium. Okay. And I may also have, for instance, some species that doesn't behave. In this case, N2, for instance. And so I have 0. It's just the general example. Of course, we could make a component matrix. So, how to build it? First, you can say, components could be chemical elements. Chemical elements such as hydrogen, oxygen, calcium, carbon, etc. And then I can say, well, if I have water, then H2O is 2 H's, 1 O. HCO3 is 1 H, 3 O's, and 1 C, etc. Also calcium, anti-calcium, etc. And if I would do multiply this U times the transpose of this, I get all zeros. Just like I've done over here. You can check it if you wish. This times this is 0, this is 0, etc. You can multiply it to all have zeros. Okay, this is one way. And this is always the most simplest way to explain what are components. So you could say that components are chemical elements. And one thing, you should be careful with it, with kinetic reactions. So here I have, for instance, silicate liquid. I have a liquid component and a solid component. I have to maintain the two because they don't react at equilibrium. Okay, this is one way. Another way is by using primary species and secondary species. Okay? So the primary species, I could say instead of chemical components, I could say, well, my components are water and HCO3, etc. Okay. And then, of course, water, it only composed of water. And bicarbonate only of bicarbonate, but let's say OH minus is water, and then I take away H plus, and I'm left with OH minus. So this is actually more used in chemical elements. Okay. But it is one way of making a component matrix. And just selecting some species that are primaries, and the other ones, that is secondary species, 3 in this case, are composed of primary species. But I could do anything more, a lot of other things. That is another one. And if we do U times the transpose of S, we have zeros. Okay, so this works as components. We could use this as components. Although I don't know, I have the faintest idea what it means. But what does this component mean? Is water plus calcium plus H plus. It doesn't make a lot of sense, but you can use it. Okay, you can work with it. Okay, now we go a little bit to the subject of this seminar, which, well, I have the liberty to make my component matrix as I want. And there are lots of different ways, but of course I wanted to do it in a nice way. Okay? And what is a nice way? Well, we have to make some definitions. Okay? First definition is what I call homogeneous components. Homogeneous components. This is a little bit in analogy to the homogeneous reactions. Homogeneous reactions are reactions of species that all pertain to the same phase. Okay? So homogeneous components are just components of which the species pertain to only one phase. Okay? So that's one definition. Another one is conservative. Conservative, it doesn't involve equilibrium or kinetic reactions. Of course, by definition, the components always get rid of the equilibrium reactions. Okay? But I say, well, if it is completely component, it doesn't involve equilibrium, neither kinetic reactions. And now with that, I can define some, let's say, nice components. Okay? Nice components are, for instance, homogeneous liquid conservative. So they are all pertain to the liquid phase, and they are completely conservative. This is nice. I can do the same for gas and the same for immobile. But yeah, I do it. I don't want to impose that it is conservative. Okay, so it would imply kinetic reactions. Actually, these are very nice reaction components. Okay? And the reason is that they behave conservatively, and they always stay within the same phase. So it is like a conservative tracer or something. So, which is very nice to, and from a numerical point of view, but also we can do something, maybe some analytical solutions. Okay? Well, of course, what shape do these have to have? Well, if they are homogeneous liquid, these, which refer to the gas into the immobile phases, should be zeros. And over here, this, well, I maintain some sort of an F part of the component matrix. Referring to this, it should be it should eliminate the equilibrium and the kinetic reactions. What that means is that this homogeneous liquid conservative multiplied, I forgot the transpose, multiplied by the acid transpose should be zero. But the same for the homogeneous gas conservative, and almost the same for the homogeneous immobile. So I say that, well, it should only eliminate the equilibrium reaction. So it should be the kernel of this submatrix of SAEI. Of course, now, how many of these homogeneous liquid conservatives do I have? Well, it's a little bit like what I've done over here. 28 is 20 plus 8. Okay. And how many should I have? Well, the number of liquid species minus the rank, my SL. And the same for conservative. Number of gas species minus the rank of Sj, of the gas part. And then for the immobile, I'm a little less restrictive. So it is the number of immobile species minus the rank of the gas. So of course, this is the maximum. So this is the maximum number of what I call nice components. The rest are, I call heterogeneous. So they can be of any phase, and they can have kinetic reactions, etc. So these are not nice. They're nasty. Nasty. Okay, so this is the theory, and then of course we can apply this to our general example. I have my liquid gases in immobile. How many liquid conservative do I have? It's a number of columns of the liquid part. 1, 2, 3, 4, 5, 6, 7. So this is 7 minus the number, the rank of my S liquid part. Okay. To be a bit careful, but in this case, this is fully ranked. So I have 1, 2, 3, 4, 5. So 7 minus 5 is 2. So I have two rows, two homogeneous liquid conservative. And automatically this is 0, and the rest is 0. For the gas in the immobile part. Can do the same for the gases. We got two columns, two gas species, and then I took the range over here. But these are all zeros, so this doesn't count, so the range is 1. So 2 minus 1 is 1. So I have 1. Well, nice gas component, homogeneous gas component. Well, I can do the same as here. I have two immobile species minus. I only have to take into account the equilibrium part, which is 1, the rank of 1, so 2 minus 1 is also 1. And the rest, 3 in this case, but they are not nice, they are nasty, heterogeneous, etc. So, this is just a way of doing this. And just some other examples, okay? This is just a lot of people will work with the decay of organic matter, okay? We can say that organic carbon is immobile, and we can do the same trick, okay? So I can, in this case, I have two kinetic reactions, aerobic decay and denitrification. And I can do the same, and then I get quite a lot of nice, homogeneous, conservative components. 4, and only 2 nasty heterogeneous reactions. So these 4 components behave as a conservative treasure. Yeah, just maybe another thing is another example is cation exchange. Cation exchange. I can do the same. So I have a reaction of sodium and calcium that get exchanged with this should be an X actually. So we have the X represents the adsorption complex, and so we have reactions between sodium, potassium, or calcium adsorbed, which can exchange with the sodium and calcium in water. Can have, in this case, these 2 reactions. And then I can do the same, and for instance, an interesting thing, the homogeneous immobile, okay, is just absorbed sodium plus absorbed calcium plus 2 times the absorbed calcium. And this is actually what we usually call the cation exchange. So actually, the cation exchange, which we usually assume that is constant. Okay. It doesn't change, but actually it is a sort of immobile component that we can deduce. This is a little bit of illustrations, and then there is always a big problem that we have in reactive transport is with minerals. Okay? Minerals, we usually assume that they are pure. So if I have calcite or gypsum, I say that the calcite or gypsum only contains calcite or gypsum. It's not mixed with other things. It is contrary to, let's say, water. And water has things dissolved in it. But usually is for mineral phases, we assume that it is a pure phase. In that case, thermodynamically, the activity of this mineral is 1. Okay, then the basic problem is that it can be, this mineral can be absent, it cannot be there, or it can be there. Okay. So if it's not there, the concentration of the mineral times, this is the theta, is the, let's say, the volume fraction. So volume fraction of the mineral, how many mineral I have per volume of medium, porous medium, times the concentration of the mineral, moles of calcite per volume of calcite. And this typically is a constant. What actually does change is this theta, the volume fraction. Okay, so recently, how many moles of mineral I have per volume of porous medium. And this, well, if it's not there, if it's absent, it's 0. And then I have the activity of the mineral, the omega of the mineral. Actually, it's the 10 to the saturation index is also something used. Saturation index. So we don't know. It could be anything. Now, if it is present, if the mineral is present, actually it's the other way around. We know the activity of the mineral is 1, because it's a pure phase, or we assume a pure phase. And we don't know the concentration of the mineral. It is something variable. We have to calculate. Okay? Now, maybe one thing, the number of components, it refers to the number of transport equations, actually doesn't change. If we do one, if it's present or not present. If we want to know the concentration of the mineral, we can sometimes do some clever things, but actually, the number of components does not change. Okay, then if we want to do reactive transport, the problem is always we have to think, let's say, about the variables. And then I can do basically 2 options. At least here I present 2 options. One option is I do my reactive transport using the concentration of these primary species as variables. Okay? Actually, I did this in my thesis, okay? In so it's also. The problem is that this means that I do have to change the variables depending whether the mineral is present or not. And actually, I cannot take advantage of these nice components. But the chemistry becomes more simple. Now, another option is to use the concentration of components, the concentration of the rho, okay, the calcium, the total calcium concentration. And actually, variables do not have to change. We can take advantage of the nice components, and the chemistry is becomes a little bit more complex. But actually, one thing, the components, the definition of components or this component matrix does not necessarily have to change. Although I did so in my thesis. But now I say it doesn't have to change. Okay. Just illustrate it by means of a very simple example. So we have 2 reactions with the calcite, and we have the calcite dissolution, and some bicarbonate H2CO3 reaction. Okay. And then we can apply this the method to get my nice components. One nice component is calcium plus H plus H2CO3. And bicarbonate, bicarbonate plus H plus 2 times H2. And then I got one, according to my definition, nasty, which is calcite minus H2CO3 minus H plus. So this is a small example. So first, if I use primary concentrations, so I write my transport as a function of primary concentrations. And my primary concentrations are, so you can see a little bit, yeah, I put it in gray, but you don't see it. So my primary species are calcium bicarbonate, and maybe this one. Okay? But I have to change it. So, if mineral is absent, of course, then my concentration of calcite is 0. And then here I put my transport equations. I got 3 components, so there are 3 transport equations, which I just wrote with all the species, okay? And of course, here there is one calcium carbonate which doesn't exist, okay? Because it's here I put for instance, some of the primary species. Okay? Calcium bicarbonate, here, for instance, I could say concentration of this. Then I have my mass action laws. Okay? My mass action laws for the 2 reactions. And first one was with bicarbonate H plus H2CO3. The other one was with calcite dissolution. And I have this omega. This omega is the saturation index, or actually the activity of the mineral. So these are the equations that I have to solve. And I just associated a variable to each equation. What I can do is to say, no, I can write the concentration of my second species, which is CH2CO3, as a function of calcium bicarbonate H+. And the same is my own. And I can just substitute my concentration of H2CO3 is a function of calcium bicarbonate H+. Okay, so that is if there is no mineral. Okay? If there is a mineral, if it is present, it's a little bit different. The activity of the mineral I already know, okay? It's 1. And of course, I don't have to put this over here in this log omega, because omega is 1, log omega is 0. So take it away. And then I can do something similar, but of course I have to change the primary species. Instead of calcium bicarbonate CH+, of course this cannot be primary in this case, because it's already 0. But in the other case, I do have to use it because I want to calculate it. Okay? So I have to put it somewhere. Okay? And I put it for a certain component. And the rest is more or less the same. Okay? But I have to change change instead of my omega, I have to put some other variable. And we can do it like this. Okay? I have to, of course, whether the mineral is present or not, I have to change the variable. Which is a sort of in the edge, that's to code this and to have an algorithm that does it correctly, etc. And another thing is, I got these two nice, theoretically nice components, but they're still not linear, coupled, etc. Because this H2CO3 is some function of my mass action law of the other primary species. So this is a term, a very nonlinear term, and as it depends on the bicarbonate or other stuff, then it's coupled to the other transport equations. So this is not, I cannot take advantage of these nice components. Okay? But the chemistry is relatively simple. Okay, now the other thing, if I use the component concentrations, okay? So I take my first two equations, which were nice ones, nice components, and if I would just write them as U1. U1 is the concentration for the first component, which are only liquids, U2 of the second. And of course, this is just linear. Okay? This is just a conservative tracer, sort of thing. Okay? So this is easy to calculate. Of course, the third one is a little bit more complicated, because it's U3, but only the liquid part is transported. Let's say transported, and the solid part is doesn't move. Okay? So I have to take that into account. So I have to write this different. U3 minus the immobile solid part. Okay. Now, of course, you can say, well, this is not very nice. But of course, it becomes, if the mineral is not there, if it's absent, no mineral, then becomes it very nice because it just U3. It's like the other ones. Okay. And if the mineral is present, this term over here becomes independent of U3. Okay. So it can still do some sort of decoupling. Okay. So actually, I would say that the nice thing is that actually I don't have to change to think about whether the mineral is absent or not. All that thing is, let's say, moved to the local equations. I can move it to the local equations. So let's first see a little bit how these local equations look like when I have to solve them. Well, if the mineral is absent, okay, then I do something similar. So actually, my local chemistry equations does not only have to take into account the mass action laws, but also the definitions of the components. U1 is the concentration of calcium plus H2. U2 is bicarbonate plus etc. And U3 is minus calcium minus plus the calcium. But the calcium, of course, is no mineral, so the calcite is 0. And then, well, I got in theory, I got 5 variables, 5 concentrations that I have to solve with 5 equations. So in theory, we can do it. Okay? How we do it is another question, okay? But we can do it. And well, just if the mineral is present, the same only, well, instead of now I have to calculate the calcium carbonate, and I don't have to calculate the omega. Okay? But of course, this is something that I can decide locally. Yeah? One calculating the local chemistry. And still 5 variables and 5 equations. Okay? Now, of course, the problem is that this may look very nice if I know that mineral is present or not. Okay? Then I can do that. But of course, very often I don't know that. Maybe I don't know whether the mineral is there or not. Okay? Of course, what I could do is sort of iterate. I could say, well, first I try this one. I do the calculations. I calculate omega. And if omega is more than 1, it's wrong. Then the mineral should be there. So if omega is larger than 1, I do something else. I repeat it, assuming that omega is 1. And then I calculate my data and how many calcite I have. If my calcite is negative, if I have negative concentration, cannot have negative concentration, then I've done something wrong, and then I go back to this one over here. I impose that I don't need calcite. And then I can do iteratively. So that's one way, to do that. Of course, there is a better way, I think, is to mathematically it's called a complementarity function. Okay? Complementarity function it's a definition. Phi is the complementarity function. So if I have phi AB, A and B, it means that if B is larger than 0, then A is 0. If A is larger than 0, then B is 0. We can also use for instance, one way to do it is the minimum. So the minimum, I say the minimum of A and B should be 0. And this is just to say, well, if A, for instance, if A is larger than 0, if I have this precipitation, if I have mineral, then B is 0, and this should be 0, and the log omega should be 0. And which means, of course, omega should be 1. And also the other way around. B larger than 0, which means that omega is smaller than 1. Did I choose that right? Yeah, then A, so there should be no minimum. So that is a way to sort of do it during calculation. And just impose another equation, okay, which represents my condition. Okay. Actually, it's quite. I would say it's more beautiful mathematically. But it's also quite simple and easy to code. Yeah, I don't have to do some sort of complicated switching between calculation when it is when the manual is present or when it's absent. I don't have to do that type of iteration. Okay, that is well, actually this is Sasha for it, who says that it should work. Yeah. I haven't tried it yet, but he says that it works. Okay, just some conclusion. There's some conclusions. We can calculate the maximum number of nice components and the minimum number of nasty components. Yeah? And of course, you have to do a little, to think a little bit about the stoichiometry. Okay, because I deduce it from my chemical system, from my stoichiometry. And just to say that mineral precipitation and dissolution doesn't require change of components, but it does imply, if you use this species, it does imply radical change. Okay, if we look at what happens when we use primary species and concentration of components as variables, and here the local chemical equations that I have to solve are rather simple. It's already said, it requires a little change, but we cannot take advantage of these nice components. Okay. So there are a few disadvantages and maybe one advantage. Of course, we can also use the concentrations of the components, and then of course the difficulty is the chemical equations become a little bit more difficult. Okay? But it doesn't require the change of variables in the transport equations, and we can take advantage of the nice components. Okay? It's also an advantage. Okay, and with this, I stop. It's already almost now. I don't know, some questions? Nobody.
Está escrito algo en el chat.